The quantum conundrum. Do all objects have both wave-like and particulate characteristics? Do fermions, such as electrons, have wave features? And does light and other types of electromagnetic radiation have particulate features? The short answer is yes, they do. This isn't science fiction. It's the strange reality of wave-particle duality. A reality that lies at the heart of quantum mechanics, governing the behavior of matter and energy at their most fundamental levels. So what led to this understanding? The best candidate for triggering the dawn of this new age of physics would be the 1887 experiments performed by Hertz on radio waves using a spark gap receiver. He observed a stronger spark when the radiation directed at electrodes passed through a quartz prism compared to a glass prism. His conclusion was that UV radiation, which is blocked by glass but can pass through quartz, caused the discharge of electrons from the metal electrodes, an observation that he found striking and yet totally puzzling. Before the 20th century, physicists thought of waves and particles as distinct entities. Thomas Young's double-slit experiment of 1801 proved the wave nature of light, since the diffracted rays underwent both constructive and destructive interference. Meanwhile, John Dalton proposed the solid sphere model of the atom in 1803, two distinct entities with no overlap in their characteristics. Hence the total puzzlement of Hertz in regards to the results of his experiment. Fast forward to the seminal year of 1905, the year of the 4 Einstein papers, the first of which, titled "On a Heuristic Point of View Concerning the Production and Transformation of Light," was on Einstein's theory that light consists of discrete packets. The quantum revolution was on the horizon. This perplexing duality shattered the foundations of physics and ushered in a new era of understanding the universe. Pioneers of duality, unveiling the dual nature of reality. The story of wave-particle duality is a tale of scientific giants. Albert Einstein, the most famous physicist of all time, played a crucial role.
In 1905, I proposed that light, long considered a wave, could also behave as discrete packets of energy called photons. This revolutionary idea explained the photoelectric effect, where light shining on a metal surface could eject electrons.
Then came Louis de Broglie, a French physicist, who took Einstein's idea a step further. He combined Einstein's famous mass-energy equivalence equation with Max Planck's energy equation to produce his wavelength equation.
In 1924, I proposed that all matter, not just light, has wave-like properties. I suggested that even particles like electrons have an associated wavelength. This groundbreaking hypothesis linked the world of particles with the world of waves.
Niels Bohr, a Danish physicist, provided another crucial piece of the puzzle. He introduced the principle of complementarity in 1927. The principle states that it is not possible to determine both the position and velocity or momentum of a particle. Bohr argued that the results obtained from studies of quantum entities are dependent on the details of the conditions of the observation, most critically, the specifics of the measuring devices used. These differences would not be contradictory, but complementary. For example, the use of electrons in the Young's double-slit experiment highlights their properties that are associated with waves. Namely, the coherent electron wave is split in two, passing through the two slits and then producing interference patterns on the screen, a characteristic observed in waves. However, the fact that electrons have a mass and a fermionic spin of half indicates their particulate nature. According to Bohr's principle, these results are two sides of the same coin, and both are necessary for a complete description of reality. Seeing is believing. Experimental proof of wave-particle duality. Hypotheses are great, but experimental proof is the cornerstone of science. As well as the repetition of the double-slit experiment with electrons mentioned previously, another crucial experiment was the Davison-Germer experiment, conducted in 1927. This experiment demonstrated the diffraction of electrons by a nickel crystal. Diffraction, the bending of waves around obstacles, is another phenomenon characteristic of waves. The Davison-Germer experiment provided further evidence for the wave nature of matter. And of course, the photoelectric effect highlights the nature of electromagnetic radiation as discrete packets of energy in photons. The quantum revolution, implications and unresolved questions. The discovery of wave-particle duality and the subsequent development of quantum mechanics has revolutionized physics. Its probabilistic nature has challenged the deterministic worldview of classical physics, forcing us to rethink our understanding of reality at the most fundamental level, with profound implications for our understanding of the universe. It underpins a range of modern technologies, including electron microscopes, lasers, and transistors, and as mentioned in previous videos, it enables the possibility of quantum computing, a revolutionary technology that harnesses the principles of quantum mechanics to perform calculations beyond the reach of classical computers. Of course, the book has not been completed. Quantum mechanics still poses many unanswered questions. The interpretation of wave-particle duality and the nature of measurement in the quantum realm remain topics of debate and ongoing research. The quantum world, with its strange and counterintuitive phenomena, continues to challenge our understanding of reality. The journey into the quantum realm has just begun. And we aim in this channel to provide clarity and detail to this fascinating field of science. So if you like this video, hit the like button, subscribe to this channel, and hit the notification bell to be alerted to all future uploaded videos. Most importantly, stay curious.